All right, it's Brian, and this week we are talking about nuclear physics. And I don't know if you've noticed, and I should have mentioned this like forever ago. Whenever I start a new topic, I have a slide, and the slide lists what I think are like the key features of the topic we're about to look at. And for nuclear physics, here's the three things. One, the forces holding the nucleus together are large, and so therefore so are the energies. Also, we have this idea that radioactivity is a natural process. And you are being exposed to radiation from naturally occurring sources as we speak, and we'll talk about that. And here's the thing, radiation and radioactivity are dangerous. We have to be aware of this, but they're also useful. And the radiation you're being exposed to right now, it's fine. These are all the types of topics we're going to talk about. This is going to be a really, really fun week with lots of amazing history, lots of interesting practical applications. Let's get started. I'm going to start actually by, if we were in class, what I would do is I would pick somebody in the class who was having a birthday, and I would give them a helium-filled balloon. And I would tell them this gift of the helium-filled balloon is more special than they know. Ooh, and Milo has come in. Hey Milo, how's it going there, bud? Oh yeah. Milo's wagging his tail, and he's wanting to know why I'm paying attention to my tablet instead of this awesome dog who's right here, but that's the way it's going to be for a short time, buddy. Anyway, I would give a helium balloon, and I would have us all sing happy birthday. So for those of you in the class who have a birthday within the next week, well, you know who you are, and there's several of you. In a class of 400, there's going to be a bunch of people with birthdays coming up. I'm going to sing happy birthday to you. Happy birthday to you. Happy birthday to you. Happy birthday, dear person in my class who has a birthday in the near future. Happy birthday to you. And I'm giving you a helium balloon, and the helium balloon is more special than you. And I'm so special. I drew a little smiley face on this balloon. Here's a little helium balloon just for you for your birthday. Now, we'll talk about why it's so special later, and it's a story of nuclear physics. Here's our intriguing question for the week. So this picture right here looks X-ray-ish, but it is not an X-ray. It's what's called a bone scan, and it's able to show us places in this person's hands where we have activity. And the activity, and because this is an older person, the activity isn't bone growth that should be happening, it's inflammation. This is evidence of arthritis, and how this works is something we'll talk about in this particular section. Now, I want to remind you of a key fact from last week, and that's this. Particles have a wave nature, and because we took these wave-ish particles and we constrained them to be in a certain region of space, there were only certain wavelengths that met the boundary conditions, and so only certain possible energies. And so we had these particle in a box states, okay? Now, we raised the idea briefly last week, but a central question is this. What happens if you make the box really, really, really small? And if the box is really, really small, the energy levels are gigantic, and the nucleus has a diameter of about 10 to the minus 14th meters. Okay, that is ridiculously small compared to the size of an atom. It's smaller by a factor of 10,000. So the box is very, very small, which means the energies are gigantic. And let's go ahead and calculate just how big they are. So think back to the particle in a box energy states, which we talked about last week. Suppose I took a proton and I confined it into a one-dimensional box of this size. Here's a question. What are the particle in a box energy states for a proton in a one-dimensional box of size of 10 Fermis? And that a Fermi is 1 times 10 to the minus 15th meters. So as we saw in the previous slide, the size of the nucleus, 1 times 10 to the minus 14th meters. So we take a proton, confine it to a box of that size, question, what are the energy states? I want you to pause the video. I want you to pull out a paper and pencil or whatever you choose to do your work on. Get started on this problem. I'll be back. Well, with this problem, we use the particle in a box energy states, which we saw before, which look like this. And it's a simple matter of putting in the different numbers. Now remember, for Planck's constant, you have to put the one in joules seconds, because I'm dividing it by mass and length squared. Length is in meters, mass is in kilograms, so I have to put in the version of Planck's constant that's in our SI units. So I'm going to get a number for En. There's the quantity right here. This is a whole bunch of constants. I'm going to compute that in joules and then convert it to electron volts. When I do that, the quantity that I put in brackets over there is 2 mega electron volts. And then that's times n squared, where n is our index variable, which takes on the values 1, 2, 3, and 4. That gives us energy levels of 2 mega electron volts, 8 mega electron volts, 18, and so on. Wow, the energy levels are indeed enormous. So what that means is when I have a transition between different nuclear states, you can expect the sparks to fly. Now, so let's go ahead and continue this discussion of the nucleus. Now, you know, and you've learned about this in previous classes, that inside the nucleus of an atom, there's protons and neutrons. The number of protons determines the element. Okay, you know that that's true. The number of neutrons determines the isotope that you get. Now, a lot of elements, and tin is the poster child for this, have more than one stable isotope. Tin has more than any other element. There's a ridiculous number of stable isotopes of tin. And if you look in the periodic table and you look at the atomic number for tin, that's 50. It says it has 50 protons. If you look at the number of neutrons it has, well, it's got numbers from a low of, right here I'm seeing 62 up to a high of 74. It's got different numbers of neutrons. The number that's right here in the periodic table is the chemical atomic mass, and we don't really care about that. We will never, ever, ever use that number, and if I had my druthers, periodic tables would not include this because we're interested in single nuclei, and there is no nucleus that has that mass. That is an average over a bunch of different things, so we're not using that. It would be like if I said, oh, here's the weight of a person, I want to know what the weight of this person is. I'm just going to use the average mass of all human beings on Earth. That just doesn't make any sense. And so we will never use that number. Never use that number. Never, ever, ever. Mentally cross it out. Do not use this. Do not use this. Now, let's keep going. What should we use for mass? Okay, it is never acceptable to use the atomic weights from the periodic table. No, 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 no. I brought this up again. Don't use that. What I can do is this. If I have uranium-238, okay, this number right here tells us the total number of protons plus neutrons. That's the mass number. And you can, as a quick and dirty estimate, just take that number and multiply it by U, which is the atomic mass unit. And the atomic mass unit is more or less the average mass of a proton plus a neutron. So if I have chlorine-35, the mass is approximately 35 atomic mass units. And that works pretty well for us. But if we need something more accurate, and we will need things that are more accurate, and heavens to Betsy, we're going to need things that are more accurate today, we can look up values in Appendix C. And actually, I might have changed to Appendix D. Heavens to Betsy, I cannot keep track of the additions to the textbook. And we look up the data in a textbook appendix, and you can see chlorine-35 actually has a mass of 34.968853 atomic mass units. This is one of the rare cases when you can use all those lovely digits on your calculator. You know that you want to. I've been advising you to round to two significant figures, but now we have to keep lots of extra digits because we're going to be taking differences of numbers that are very close. So you've wanted to use those numbers. Oh, now it is your time. Let's just do a quick review, and this is stuff you've seen before. Okay, lithium, beryllium, boron, carbon, there are isotopes, not necessarily stable, but there are isotopes of each one of them that has an atomic weight of 11. So here's my question. How many neutrons are in each of the following nuclei? I want you to pause the video. I want you to think about it. I want you to answer that. I'll wait. And of course, you know the number at the bottom. Lithium is atomic number 3. That says it's got 3 protons. Beryllium is atomic number 4. It's got 4 protons. Boron's got 5. Carbon's got 6. So the difference between the weight, that's the total number of neutrons plus protons, so that's neutrons plus protons, and the number of protons, which is the number at the bottom, the difference is just the number of neutrons. So if I look at lithium it's got 8 protons. If I look at beryllium, it's got 7 protons. If I look at boron, it's got 6. And if I look at carbon, it's got 5. I'm just looking at the differences. And you know this. This is review for you. Now, mostly in this course, we're going to be talking about unstable isotopes or radioactive isotopes, but it turns out there are occasions when we're going to use stable isotopes to solve problems. And let's look at an example. So water, and you know this, is made of 2 atoms of hydrogen and 1 atom of oxygen, but the oxygen has 2 stable isotopes. There's oxygen 16 and there's oxygen 18, and oxygen 18 has 2 more neutrons. It's heavier. So if you make water, you're going to have heavy and light water. You're going to have like the water with oxygen 16. It's going to be lightweight. You're going to have the water with oxygen 18. It's going to be relatively heavy. So ocean water is a mix of those 2 species. And it turns out, and it kind of makes sense, that it's going to take more energy to take a heavier atom and put it in the atmosphere. So if you're looking at evaporation of water from the ocean, it's always true that the water molecules that contain oxygen 16 are going to evaporate more readily, but that difference is less pronounced when the temperature is high. So when the temperature is high, you're going to have relatively more oxygen 18 evaporating. When it's cooler, you'll have relatively less. So this is an ice core from Greenland, and you can see in the background there's this ice core, and you can see there's regions where I've got dark ice and then I've got light ice next to it. Those are different layers that were laid down in successive years. So if we look at the ice that was laid down in successive years, we can see there are years where there is more oxygen 16, and that means it was colder, and years where there is relatively more oxygen 18, and that tells you that it was warmer. Now, if you look at the data and you look at the water that's laid down in these ice cores, and that's water that has come from the sky, water that's come from the sky is always deficient in oxygen 18 relative to ocean water. And so the numbers here are always negative. There's always a deficit of oxygen 18 in ice that is laid down. But in some years, the deficit is more pronounced. And if you look at this graph, this is the years before the present. Look at the years before the present. And what you see is, like right now, here we are. And then there was a relatively warm period. And then, whoop, that was the previous ice age right here. And so you can see at some point we descended into an ice age. And then in the recent past, it's jumped up. So if you look at people who are arguing about past climates, how do they know what the temperature was 100,000 years ago? Ice core data, and ice core data from Greenland and Antarctica, et cetera, agrees with each other. We know very, very well what the temperature was in the past. I want to give you a chance to do a quick calculation. Now, it turns out the chemical atomic mass, the one in the table, is because you have a ratio of different isotopes. You have an average of the amounts of different isotopes that are there. And you can get a quick estimate as to how much of each isotope is there by looking at the chemical atomic mass. So for instance, look at boron, atomic number 5, and it's got 2 stable isotopes, which have atomic mass number 10 and 11. If you look it up in a periodic table, the chemical atomic mass is listed as 10.81. So here's my question for you. What is the approximate fraction of each of these 2 stable boron isotopes found in nature? Take a minute, pause the video, do a quick calculation. I'll be back. And of course, you know this. It's 10.81, so it's closer to 11 than it is to 10. So I'm going to have more 11 than 10. And if you just do a quick ratio calculation, you can see the result should be this. 80% of boron 11, 20% of boron 10, and you end up with an atomic mass of 10.81. Now let's think about what holds the nucleus together, because in some degree it's kind of surprising. If you look at the nucleus of an atom, it's made up of 2 protons, which are positively charged, that repel each other, and 2 neutrons, which basically don't participate in the electrostatic force. So this nucleus wants to push itself apart like crazy because there's this repulsive Coulomb force between the neutrons between the protons. And so as a consequence, there must be an attractive force, and it is, and it's called the strong nuclear force, and it's called the strong nuclear force because one, it's strong, it's stronger than the Coulomb force, and two, it operates in the nucleus. Okay, so it's not a very clever name, but doggone it, it's our name, we're going to stick with it. And it turns out you can have stable combinations of neutrons and protons. You have to have just the right mix to balance the attractive force and the repulsive force. And helium, a helium nucleus, is a very, very stable combination. Now, it turns out helium is atomically very stable as well. You have a closed shell. You know that. Same is true in a nuclear sense. We have basically closed shells for neutrons and protons. So 2 electrons, 2 protons, 2 neutrons, way stable chemically, but also the nucleus is very stable. Now, not all nuclei are stable. And this is a graph of every single nucleus that exists. And here's a graph on the horizontal axis, the proton number, and on the vertical axis, the neutron number. And as you can see, this graph basically, if you look at all the nuclei, there's a general upward trend. Okay? And what that tells me is, as the number of nuclei goes on, you have to have relatively more and more neutrons to stabilize it. So heavier atoms are going to have more neutrons in the nucleus than the lighter ones. And if you look too, there's a zone of stability. The blue dots are the stable nuclei, and they all cluster near this black line. That's my zone of stability. If I have nuclei below the line, they have 2 neutrons for stability. Nuclei above the line, too many neutrons for stability. One's near the line, just right. Except you end up with this region, and you can see bigger than atomic number 82, there are no stable nuclei. And the problem with nuclei that are that big is there's just so much repulsive force between all those scampy protons. There's no way to put in enough neutrons to kind of like make the whole thing hang together. And so they're unstable because they're just too darn big. And that means they're going to fall apart. And that's something we'll talk about in a future slide. Now let's look at energy levels in the nucleus. And if you look at this energy level picture, it's very much like energy levels that we've seen before with 2 differences. One, the scale is in mega electron volts, so the energies are gigantic. And also, 2, instead of just having levels for electrons, I've got separate levels for the neutrons and for the protons because they're different and they're each going to have their set of energy states. Now for light nuclei, the levels are basically at the same level as each other. And if I build up a nucleus by putting particles in it, I just put in protons and neutrons, and I can put them in up to the number which is recorded right here. So if I'm building a nucleus, I'm going to build 1 proton, that's hydrogen. If I have hydrogen 2, deuterium, I stick in a neutron as well. If I want to make helium, I have a second proton, and to stabilize it, I put in a second neutron. And you can see I put in one with spin up and one with spin down. And now you can see I've got closed shells for the neutrons, closed shell for the protons. This is an exceptionally stable combo. But let's look at other nuclei as well. And there's some nuclei that aren't stable. So let's take a look at this one. Beryllium-11. That was something we talked about on a previous slide. It turns out it's not stable. And we can look at the energy level picture and we can figure out why. If I look at the protons, I built up 2 in this state, and I've got 4 in this state. Now look at the neutrons. I got 2 in this state here. I got 4 in this state here. It's a filled shell, okay, because that level is completely full. So my extra neutron, because I have to squeeze in 7 neutrons, because 7 is the difference of 11 minus 4, my 7th neutron has to go in this upper energy level state. And the neutron says, doggone it, if I could turn into a proton, I could fill in this energy state right here. So if I could switch a neutron into a proton, there would be a decay that would lead to an overall lowering of energy. And in fact, that happens. What will happen is that neutron will drop into the proton level. The neutron turns into a proton, and it does that through the emission of an electron. And here's the equation for it. Beryllium-4 turns into beryllium-11 turns into boron-11 plus an electron. And you can see the number of neutrons plus protons has stayed the same, but the number of protons has incremented from 4 up to 5. There's one more proton than there was previously, and this is so-called beta decay. Gives off a high energy electron. And I put the electron, I wrote it like this, 0 and 1, because I'm going to let that number down here represent the charge. And then I have something which I can balance like a chemical equation. I had, on the left side of the equation, I had 4 positive charges. On the right side, I got 5 positives plus 1 negative. And so I have overall balance in charge. The top number is the number of nucleons, the number of neutrons plus protons, and it turns out that number is conserved as well. On the left, 11 nucleons. On the right, 11 nucleons. And so I have an equation that balances, and you can balance those nuclear equations just like you can balance chemical equations in chemistry. Now let's do that once more with feeling. So neutron wants to turn into a proton, and if it does that, it lowers the overall energy state of the nucleus. And it does that emitting an electron, and here it goes. And it fires out an electron with really, really high kinetic energy because the neutron dropped from a higher energy state to a lower energy state. When it did that, lost a tremendous amount of energy. Where does that energy go? It goes to the emitted electron. So this electron is coming out of here with the very, very high speed. It's traveling at relativistic speeds very, very fast. Now, here's some other types of decay modes you can have. If you have a nucleus which is just too big, and an example is uranium-238, it's just too big, it wants to break apart, and it will do that by basically throwing off a chunk. And a preferred chunk to throw off is an alpha particle. An alpha particle is just a helium nucleus, 2 protons and 4 nucleons. And we saw before that was really, really stable. So uranium-238 sheds 2 protons and 2 neutrons, so it sheds 2 protons and 4 nucleons. And as a consequence, it turns into thorium-90, because 90 is equal to 92 minus 2, and it's thorium-234, because 234 is 238 minus 4. So I just balance those equations similarly, and that's what will happen to uranium-238. It turns into thorium-234. Now it turns out, and I want to bring this up, if we look at radioactive decay, when atoms decay, they don't just disappear. So if you take a sample of uranium-238, and that's a chunk of uranium ore, it decays into thorium, which is used in welding rods, which is kind of cool in other places. But it also turns into helium because it gives off alpha particles. Now, the alpha particles come out at very, very high speed, and that's why we call them alpha particles. But in fact, an alpha particle is just a helium nucleus. If you look at the Earth's atmosphere, there is no primordial helium in it. All the Earth's original helium is gone because the atoms are very lightweight and they're moving fast enough that they actually escape from the Earth's atmosphere. So any helium that exists right now in the Earth's atmosphere, or any that exists on Earth, is not from the original Earth. It was produced by the decay of uranium in the Earth's crust into thorium, giving off alpha particles, i.e. helium nuclei. And there are places in the United States where under the ground natural gas gathers in caverns, but also what gathers in caverns is helium because there's a fair amount of uranium in the rocks, and when the uranium decays, it produces alpha particles. And so inside the natural gas there is helium, and when they liquefy the natural gas, there's a fraction that doesn't get liquefied. It is helium gas, and it's put in tanks, and it's used to fill up balloons for parties. And here's the thing, this process that produced this has been happening for 4.5 billion years. The helium in that balloon, which I gave to a person at the start of class today, has been under construction for 4.5 billion years, but the story is worse than that because that uranium was actually created 6 billion years ago in a cataclysmic explosion in our neighborhood. And so the helium inside that balloon, that is special stuff. That is the collection of alpha particles from dying uranium nuclei that has taken place over 4.5 billion years. It's been lovingly trapped underneath the surface of the Earth. It was tapped, it was put in a tank, it was delivered to a store, it filled up a balloon, and it was given to you. So happy birthday. And this balloon is so special because it's full of helium. I let it wear a matching cap to me just because I wanted it to feel extra special, as I want you to feel extra special on this, your extra special day. Now, let's talk about the other kind of decay. If I have nuclei, they can be in excited states, just like atoms can be in excited states. And when they drop from a higher energy state to a lower energy state, they emit a photon. But since the energy levels are so far apart, the photon that emits, this is one badass photon here. This has a really, really high energy, not electron volts of energy, but mega electron volts of energy or kilo electron volts of energy. And frequently this happens when I have a beta decay. I have like molybdenum 99 when it decays into technetium 99. When it does that, the technetium is in an excited state, and then it subsequently decays through the emission of a high energy photon, i.e. a gamma ray. Now, I have been talking for far too long, and it is time for you to pause the video and do some calculations. And we're going to do that by determining the daughter nucleus of some decays. So strontium 90, when it decays, what does it turn into? And strontium is atomic number 38. Radon 222, that's atomic number 86. When it decays by alpha emission. What does it turn into? I want you to take a minute. I want you to solve both of those little calculations. I'll be back. Now let's think about this. Strontium 90, when it decays through beta emission. So the number of neutrons plus protons doesn't change. So whatever X is, it's got a number of protons plus neutrons that's 90. But how about the atomic number? Well, it turns one neutron into a proton. So the atomic number goes up from 38 up to 39. So what we have is yttrium 90. For radon, okay, it loses 4 neutrons plus protons because it loses 4 nucleons. So you end up with an atomic weight of 218. How about the atomic number? Radon is 86. Well, when you lose 2 protons, you end up with atomic number 84. So when radon decays, it decays into polonium 218. Okay? So first I have yttrium 90 is my first one, and for my second one, I have polonium 218, so the daughter nuclei of the two decays. Next up, if we give you the parent nucleus and the daughter nucleus, we want you to determine what type of decay it is. So cesium-137 decays into barium-137. What type of decay is it? How about thorium-230? It decays into radium-226. What type of decay is that? I was going to say talk with your neighbors. Well, do talk with your neighbors. Heck, call them up and say, Brian just asked me to talk to you. Or you can talk to your literal neighbors. You can go out into your backyard and shout over the fence from a respectful distance of at least 6 feet. But go ahead and cogitate on this one. What is the decay mode of the following decays? I'll be back. Well, cesium-137, okay, it turns into barium-137. The number up top here, the atomic mass number, hasn't changed. So that tells me it hasn't lost protons or neutrons. It is not an alpha decay. It is not an alpha decay. And the number, cesium, atomic number 55, has gone up to barium, atomic number 56. That says it picked up one more proton. Where did it do that? By getting rid of a neutron. So one neutron turns into a proton. This is beta minus decay. How about this one? Thorium-230 turns into radium-226. Well, the top number goes down by 4. It's lost 4 nucleons. That is a clear signal of alpha decay. And here's another way to see it. Thorium, atomic number 90, turns into radium, atomic number 88. That's 2 fewer protons. So the number of protons goes down by 2. The atomic mass number goes down by 4. We are good to go. Now, I want to do an energy level diagram, and I want to look at boron 12. And I want you to sketch the energy level structure for the neutrons and the protons. And the question is this: what decay mode would you expect for this nucleus? So go back, like we did before, and sketch. Go ahead and build up the energy levels of the neutrons and the protons. Build this nucleus up. And then think, is there a way it could become more stable? What type of decay mode would it be? Take a minute, sketch this out. I'll be back. Now let's do some building here. So boron is atomic number 5, so it's got 5 protons. So when I build up the proton levels, it looks like this. I can stick 2 protons in this level, and I can stick 3 protons in this level. Now this one can take up to 4, so what that tells me is I've got a spot here where a proton could fill. And if I fill up the neutrons, I get 2 neutrons here, I get 4 neutrons in the next level. I got to put in a total of 7 neutrons because boron 12, it's got atomic number 5, and so clearly it's got 7 neutrons. My 7th goes up here, and that tells me this is a prime candidate for beta minus decay because this neutron can turn into a proton and fill up that energy level. In fact, that's what happens. This will be a beta minus emitter because the neutron can turn into a proton. I get a beta minus decay. By the way, I'm just going to take a quick pause for a moment, and you have seen our learning assistants roaming the room, helping people learn physics, answering questions, providing clarification, etc., etc. Here's Laura and Eric, and you're asking yourself, I like physics so much. Is there a way that I can continue next year being part of the physics experience? The answer is absolutely. I'm looking for LAs for next year. I want you to check the link on Canvas if you're interested in taking part next year as a learning assistant. Go ahead and check it out. I hope you do. Now this picture right here is a photo of a piece of developed film that had spent it was in Henri Becquerel's desk, like back in the 1800s. He had this piece of film in a light protective wrapper in his desk drawer, and he put a chunk of uranium ore on top of it. And then at some time later, he exposed the film, and the film had these dark spots on it where it had been exposed by something that came through the wrapper. And what it was radiation being emitted by the uranium. And this was the discovery of radiation. And then it subsequently became clear that as this uranium was emitting this radiation, it was also turning into different elements. This was the discovery of radioactivity. Radioactivity was discovered. And I want you to pause for a minute and look at the properties of radiation. We have this video, actually we have a couple of videos online that talk about cloud chambers. And when you have radiation from a radioactive nucleus, it gives off these ionizing radiation, alpha particles, which are helium nuclei moving very quickly, or electrons, which are moving very, very quickly, or gamma rays. And those ionize matter, and where they ionize matter, we can make clouds form. Go ahead and take a look at our 2 cloud chamber videos. One is a more recent one made for your class, and the other one was from a television show back in the day. And the person who's in the video, what a little cutie, he's actually a CSU student right now, just getting ready to graduate. Now here's a version of this that I made myself. I took this uranium glazed plate, and you saw that in a video, or you'll see that in a video I'm going to make this week. Okay, uranium glazed plate, I took it and I stuck it on top of, you can see a key here, and a paper clip, and some coins, and I took those and I put them on top of a piece of Polaroid film, stuck a piece of uranium glazed pottery on top of it, and I made my own radiograph just like Henri Becquerel did. And I was able to do that because the radiation emitted by those radioactive substances is ionizing radiation. It exposes film. It does other things as well. It will give you radiation burns, and the radiation burns are because it's ionizing tissues, it's destroying DNA, it's bad. It's a bad, bad, bad thing. It also lets us detect the radiation. And you've read about that in the textbook. This is how a Geiger counter works. And in the video, the key concept video about radiation and radioactivity, I show how a Geiger counter works. But basically, ionizing radiation comes in, ionizes atoms, and you collect the electrons, and you get the click when I have a discharge inside the tube. Now, if we look at the different kinds of radiation, alpha particles, not very penetrating at all, and you can see that in the video. Gamma radiation, much, much, much more penetrating. And the alpha particles, they're helium nuclei, they're big, they're really chargy, they ionize like crazy and then slow down and stop, don't go too far. Beta particles are kind of in between. And I want you to take a look at this video, there's a key concept video about radiation and radioactivity. You can see the penetrating abilities of the different kinds of radiation. You can see different sorts of radioactive substances and the operation of a Geiger counter. So take a moment, take a look at that key concept video. We'll be back. Now, radiation is part of your life because, as it turns out, there's a fair amount of uranium in the soil, and uranium has a really long half-life of like 4.5 billion years. So the Earth had a bunch of uranium in it when it was formed, and a bunch of it is still there. It's got a long half-life, and the uranium decays this long decay chain right here. And when the decay chain gets to radon, okay, radon gas actually radon is a noble gas. So the ones up here, they're all metals. So if I have rocks in the soil, uranium stays there, thorium stays there, et cetera, et cetera. When it gets down to radon-222, it's a gas. It will percolate out of the soil. So right now, as the ground is thawing, radon gas is percolating up through the soil. And near the surface of the Earth in the springtime, you can measure significant quantities of radon-222, and that is a radioactive gas, and it decays into these short-lived progeny right here. And these are very short-lived atoms that are kind of like, when the radon decays, it produces them. Radon's in the air. Well, these are metal atoms. They don't like being in the air. They glom onto an existing dust particle, and you can gather the dust and you can detect it. That's something I talked about in the video. But you are exposed to radiation as part of this. And Colorado has a fair amount of uranium in our soil. So this is actually a significant component of the radiation you will receive in your lifetime. It also means you're going to get increased radon exposure in the shower because it turns out radon, like all gases, dissolves in water. And so when the streams start running, they're kind of like going downstream. They will, and radon gas is percolating up out of the soil. Radon will be dissolved in water, and when you heat the water up, some of the gases will come out of solution. And I have measured this in my bathroom. I've run a Geiger counter and then turned on an ice hot shower, and the count rate on the Geiger counter goes up when the shower is running because there's radon gas that comes out of the water, which is crazy. Here's the thing. You're going to be exposed to radiation anyway. It's part of your life. It's already happening. Don't worry about it. It's low levels. It is not a danger. Do not stop taking showers, particularly in this era of social distancing. We need to stay clean. I mean, even though people aren't getting close enough to smell you, you got to keep yourself tidy. So keep taking showers. Don't worry about that. I just want you to know it's a thing. Radiation is already part of your life. Now, another property of decay is a random process, and I've used to illustrate that with a coin flip. Individual atoms, in every interval of time, they decay or they don't. They don't age. Every atom is identical. It's indistinguishable from every other atom. You can't tell, like, if I have older or I have younger ones, just every unit of time, they have a certain chance of decaying. And because of that, the form of the decay is an exponential decay, not like the exponential growth that we're seeing in these coronavirus days. You've seen so many graphs like this. And one of the really good things that I hope comes out of this coronavirus thing, which is terrible and all kinds of awful, one of the good things I hope comes out of it, because there better be something that good comes out of it, is that people have a better understanding of exponential functions. Anyway, this case, radioactive atoms, you're going to have an exponential decay. It's going to have this particular form, and the form works like this. Every half-life, the number of atoms decays by half. So if I start with the number of atoms N0, 1 half-life, I got half of that. 2 half-lives, I've got a quarter. 3 half-lives, I have an eighth, and so on. Here's the basic relationship for calculating the decay of the number of atoms. Now here's a pro tip. Sometimes we list the activity, or we give you the number of atoms. Sometimes we give you the mass of the atom. Sometimes we give you the activity. There's some sort of a ratio of what it was and what it is, okay? And you're going to use that to do your calculations with. And I think you'll see how this comes out in practice. And here's an example. Back in the 1980s, there was this nuclear reactor accident in what was then the Soviet Union, what's now the Ukraine, actually. And this Chernobyl nuclear reactor released ridiculous amounts of radiation into the air, and it's really problematic. We'll see later that when you have nuclear fission inside a nuclear reactor, you get these short-lived isotopes, and one of them was iodine-131. Iodine-131 has a half-life of 8 days, and it's particularly worrying because it concentrates in your thyroid gland. And also, it's really easy to take it up from the environment. It turns out it settles on grass. Grass is eaten by cows. Cows make milk, and the milk has lots of iodine-131 in it. Well, when this happened, the Soviet authorities didn't say, oh, we had this big nuclear accident, here comes a cloud of radioactive debris heading your way. They kind of said, what? What reactor accident? No, nothing bad happened. No need to look over here. So by the time they admitted it and it was clear what had happened, farmers had all kinds of jugs of milk from cows that had been eating the grass. And the milk had lots of iodine-131 in it. What do you do with that milk? The answer is you make cheese out of it, because if you take cheese, you can let it sit on a shelf. And when it sits on a shelf, the iodine-131 will steadily decay, and at a certain point, it will become safe. So here's my question. If you had a sample of milk and you use it to make cheese, how long would you have to store it until the number of atoms drops to 3% of the initial value? I want you to think about how you would solve that problem. I want you to sketch it out. I'll be back. Let's go ahead and get this one started. Now remember, our basic relationship is this. N is equal to N0 times 1/2 to the T over T1/2. That's our basic relationship. And I don't know N or N0, but what I do know is a ratio. I know N over N0. N over N0 is equal to 1/2 to the T over T1/2. And I know what N over N0 is. It's 3%. So this is 0.03. And I know what I don't know what T is. That's what I'm looking for. But I know what T1/2 is. That's 8 days. And here's another pro tip. I have T over T1/2. I don't care what unit that's in. Could be seconds, could be minutes, could be days, could be years. I just care that the two units, two quantities, T and T1/2, are in the same unit. So if I put in 8 days, I'm going to calculate for T1/2, I'm going to calculate a value for T that is in days. And if you do that and you complete the calculation, what you get is you get a time of 40 days if you round it to the nearest day. And let's just see if that makes sense. If I start out with, let's say, 1,000 atoms, 1 half-life later, I have 500. Actually, let's back this up. Let's just do 100 atoms. So I start with 100 atoms. That's my 100%. 1 half later, 50%. 2 half-lives, 25%. 3 half-lives, 12.5%. 4 half-lives, 6.25%. 5 half-lives, 3.125%. Oh, and 3.125 is approximately equal to 3. So that's telling me 1, 2, 3, 4, 5 half-lives. A half-life is 8 days. 5 half-lives, 40 days. My assessment, all systems go. Now, it turns out when they did this, people actually did this with their milk and made cheese. The cheese was no longer dangerous because the only reason the iodine-131, iodine's not dangerous. They add it to salt. And what it decays into is not dangerous. The problem is it was radioactive. And after that amount of time, there were no longer dangerous levels of radiation. You can feed it to your children. Now, you can also use the number of number that you have of different isotopes to do radioactive dating, and I'm sure you're familiar with this idea. Okay, this scrap of parchment from the Dead Sea Scrolls, and this very scrap actually was found to have a carbon-14 to carbon-12 ratio that is 79.5% of the modern value. My question is, what is the age of the parchment? And you're going to use the fact that the carbon-14 is decaying, the carbon-12 isn't. You've read about in the textbook that while things are alive, the amount of carbon-14 stays essentially constant. But when things die, the carbon-14 starts to decay, and so the relative fraction of carbon-14 goes down. So parchment, this is animal skin. When it was on the animal, the amount of carbon-14 was constant. As soon as the animal died, that carbon-14 started to decay. This is the ratio of the carbon relative to the modern value. How old is the parchment? I want you to do that calculation. I'll be back. And before I give you the answer, let's just talk about how to write it, okay? So remember, our basic relationship was n is equal to n0 times 1/2 to the t over t 1/2. Okay, we know that that's true. But if I have n over n0, that's the ratio of the number of atoms to the number that I had originally. And since the C14 to C12 ratio is 79.5% of the modern value, what that tells me is I'm retaining 0.795 of my original carbon-14. So n over n0 is just 0.795. With that in hand, you can calculate what t is. That's what I'm looking for. To do that, I'm going to have to do logarithms. And so remind yourself about how you do that kind of calculation. Go back, complete your calculation, and what we get is we get a time of about 1900 years. And these are the Dead Sea Scrolls. And if you know anything about the Dead Sea Scrolls, that's about the right age for them. So our assessment is all systems go. Now, activity is the rate at which the atoms are decaying. So activity, and we usually measure that by using a Geiger counter, and you can measure every decay gives off a charged particle. You can detect it. If I'm looking at the rate of decay, that's the number of atoms that decay every second, we use the symbol R for it. The number that decay is 0.693 divided by the half-life times the number of atoms. Okay, that's how you relate the activity to the number of atoms, because if I have more atoms, I have more atoms decaying, and then as time goes on, I will have less, and the decay of the activity is the same as the decay of the number of atoms, because the activity is just proportional to the number of atoms. And that's usually how you measure, that's usually how we would do these kinds of things. If we gave you a short-lived isotope in lab, that's how you would measure its decay. You'd measure the activity. Now, I want to use this concept of activity and the decay of activity to consider this question. Okay, it turns out my watch, and I have a picture of me wearing my watch right here. This watch, I got this in 2004. I've had it for a while, and the dial isn't energized. Like, this is a glow-in-the-dark dial, and normally for a glow-in-the-dark dial, it would be energized by phosphorescent. You'd have phosphorescent material, glow-in-the-dark material. You charge it up during the day, and then at night it continues to glow. But mine is actually charged up. The glow is produced because inside the phosphor on the hands, there is tritium. And tritium is radioactive, and when it decays, it basically energizes the phosphor, and so my watch will glow all night long. Even if it's been in the dark, my watch is always glowing because the energy comes not from stored sunlight, it comes from decaying tritium. But here's the problem. As time goes on, it gets less and less bright because the tritium only has a half-life of 12 years. When I initially got it, it had an activity of 100 megabecquerel. An activity in units of becquerels, 1 becquerel or 1 BQ is equal to 1 decay per second. So it had 100 million decays per second. What is the activity at present? We're going to calculate that. By the way, too, the beta particles are extremely low energy. They never make it out of the watch. And so I'm exposed to precisely 0 radiation from this. Not a problem. But had 100 megabecquerels. What is it now? I want you to go ahead and start that calculation. I'll be back. When the relationship we're going to use for this is basically the same relationship we used previously, except instead of having the number of atoms and the initial number of atoms, I have the decay rate, the activity. And the activity originally and the activity now are the numbers here. And we're using the R instead of the N. And we know what the values are. The original activity was 100 megabecquerels. MBQ. The current activity is what we're looking for, Oh, and I have everything I need. I have a half-life of 12 years, and T is the time since there's elapsed since it was 100 megabecquerels. It's 2004. That was 16 years ago. Oh my goodness, was it? It seems like it was just yesterday. Anyway, so this is the decay of the activity. And if we do a calculation, we get about 40 megabecquerels. And that would imply to me that's about 40% of it was originally. So it says my watch is shining about 40% as brightly as it did. And that sounds about right. So my assessment is, yep, seems about right. Now next time we're going to talk about how do you get energy from the atom and what could you use that for? And this is a civil defense photo from the 1950s. That's part of a story that I'll talk about later. I apologize for talking so much during this set of slides. This is a really long set of slides with a lot of Brian, and I apologize for that. Next time, I promise you a lot more opportunities for you to be active. I'll be back next time.